Hi everyone, myself Ramasamy Subramaniam, Assistant Professor in the Department of Mathematics, Madanapalle Institute of Technology and Science. Now I am going to talk sliding mode control design for wind energy conversion system. So this is the my outline of the presentation. First we see the stability analysis of the dynamical system, then permanent magnet synchronous generator based wind turbine model. So based on that model, we'll see how to modeling of the BMSG. Then that model is nonlinear model. So by using the DS fuzzy approach, we are going to convert into linear submodels to investigate the stability analysis of the dynamical system. So I used the integral type sliding mode control. Finally, based on the theoretical result, we'll see simulation examples. Finally, we'll see conclusion. The main significant result of this presentation can be summarized as follows. By introducing double orthogonal complement and propagation theorem, the continuation condition of the fuzzy sliding surface is presented. The obtained sufficient conditions of passivity and pacification criteria are characterized in terms of linear matrix inequalities, and by utilizing fuzzy Lyapunov functional passivity analysis. Given the system matrices in the DS fuzzy system and the matrices G and K in the fuzzy integral sliding manifold function, determine under what criteria the fuzzy sliding mode dynamics is passive. Then we'll see about sliding mode control law synthesis. By constructing an appropriate fuzzy integral sliding mode control, the reachability of the nonlinear sliding mode dynamics is ensured in the appearance of disturbance signal. Finally, a numerical example is provided to show the applicability of the concerned PMSG model. So, there are two ways we can study the stability analysis of the dynamic system. So, the first one is the Lyapunov indirect method, second one is the Lyapunov direct method. So, the Lyapunov indirect method stability analysis, which is based on linearization of the nonlinear system in the velocity of the equilibrium state. Only local stability of the nonlinear system. So it has some disadvantages if some eigenvalues are zero, then we cannot draw any conclusion about stability of the nonlinear system. It is valid only if the initial conditions are close to the equilibrium point. So that we are using Lyapunov direct method, the stability analysis which is based on energy functions. Answer stability nonlinear system without explicit solving dynamic equation. Easily handle the dimeering system. Derive the delay dependent condition for asymptotic stability. Determine the region of the asymptotic stability or the domain of attraction of an equilibrium. For that, let us consider the following linear system x dot of t equal to a into x of t. Here A is the system matrix and x of t is the equilibrium of x of 0. For the system, we choose the Lyapunov functional candidate V of x of t equal to x transpose of t px of t. Here, b greater than 0, that is symmetric matrix. To take the time derivative of the above Lyapunov functional v dot of t, so we get the following equation number 2. So based on Lyapunov equation, given any q greater than 0, there exists a matrix b greater than 0 satisfying A transpose b plus ba plus q equal to 0. Hence, v dot of t, we get a p plus A transpose b, that is minus q less than 0, that is v dot less than 0. We say that it is asymptotically stable. So for the above theory, so I gave a numerical example. So let us consider the A matrix. So by using MATLAB LMI toolbox and solving linear matrix inequality, AB plus A transpose B less than, we get the following positive definite matrix. So P, for this AB plus A transpose B, we get less than 0. This implies that the given system is asymptotically stable in the sense of Lyapunov function. So this is the outline of my presentation. So first we can consider the dynamic model. So to investigate the stability analysis of the dynamics models, we can construct the Lyapunov functional V into x of t greater than 0. So by using ordinary derivative, so we are finding the derivative of the Lyapunov function. So we get V dot of t. If V dot of t less than 0, less than 0, so we have to less than 0. So we have to go numerical example. If it is greater than 0, we have to construct again Lyapunov functional. This is a trial and error method. So by using the numerical example, so if the LMAs are feasible, we can find the maximum stability region. If the LMAs are infeasible, again we have to construct the Lyapunov function. So for that, so I considered the nonlinear system x of t equal to f of x of t u of t, y of t equal to g of x of t u of t. Here, f and g denoted by Lifshitz functions. X of t and u of t denote the state and control input of the system. Y of t represents the output of the system. For that, I have chosen BMEG based wind turbine system. BMEG based wind energy conversion system are brought into bring in various applications because of the reward in higher efficiency and lower maintenance cost compared to other generators such as DFG. Therefore, it is essential to investigate the wind turbine system components that contain electric generators and controllers which are playing an important role in energy conversion system. So let us see the following model. So here the rotor side is connected with blade. The right side is generator side. So these parameters denoted by the following table. So first let us see the wind turbine model construction. So a wind turbine has rotor blade and generators. This linger this linear kinetic energy has been converted into rotational kinetic energy by rotor blades. Also, with the help of generator, rotational kinetic energy has been transformed into electrical energy. To obtain the efficiency of this energy conversion, the concerning energy present in the wind need to be obtained. The turbine performance coefficient is denoted by Cp and P turbine. Here, the air density is denoted by the rho and the wind velocity is represented by Vm and the radius of the wind turbine blade is denoted by R. Denoted by R. The tip speed radius is represented by lambda. Here, Cp is the power coefficient. Pitch angle is represented by beta. The mechanical torque of the wind turbine is denoted by Tw and wind turbine speed is denoted by Wr. Torque coefficient is denoted by Cpu respectively. Now let us see the modeling of the BMSG. The dynamic model of BMSG on the DQ axis represented as follows and its parameters are listed the following table. Here LD and LQ are D and Q axis inductance. ID and IQ are the Q axis current and D axis current respectively. UD and UQ are control signals. Pi denotes magnetic flux of the permanent magnet. Beta denotes the friction coefficient of the mechanical system. Also, the electromagnetic torque is denoted by dE. Here, WE equal to NPWG, where NP denote the number of poles. The scheme of the PMSG based wind energy conversion system are represented in the following. These parameters we used to construct the wind turbine model. So the moment of inertia is denoted by J, rotor radius is denoted by capital R, air density is denoted by P, magnetic flux linkage denoted by pi, stator inductance is denoted by LQ and LD, stator resistance denoted by RS, number of poles denoted by NP, maximum power coefficient be denoted by CP max, rotation speed of the generator is denoted by WG. By model transformation with the above parameters, the wind turbine system with the BMEG is denoted by the nonlinear model x dot of t equal to A into x of t into x of t plus b into u of t. X of t is denoted the state vector x1 of t, x2 of t, x2, x3 of t, that is WG, ID, IQ. The control input is denoted by the u of t, that is UQ, UD. Here the system matrix A and B has been given the below. Here it can be stated that the above system is nonlinear model due to the product of the states. Yes, we know that the stabilization of the nonlinear model is very difficult and complex. So by the way, the nonlinear BMSG based wind turbine model can be redesigned into corresponding linear submodels by utilizing fuzzy membership function. In the real life model, the nonlinear disturbance are playing a major role in BMAG based wind turbine system due to complex environment. Therefore, we have taken the nonlinear function Fm and external disturbance W in the above system. Now, let us introduce DS fuzzy modeling. Let us consider the following nonlinear model. If theta I1 of t is neta I1 of t and etc. theta p of t is neta ip, then we get the following model. Here, neta I1 etc. neta ip are fuzzy sets. The premises variable are denoted by theta I1 etc. theta ip and R denotes the number of fuzzy rolls. Disturbance signal is denoted by W of t, which belongs to L2 of 0, infinity. The system matrices AI, BI, CI, DI are known matrices. Here, F is a nonlinear perturbation which is bounded by following relation. Here, k greater than 0, which is known constant. By applying fuzzy rule, the nonlinear system is described as follows. Here we get the linear submodels. By using the membership function hi of theta, we get here hi of theta greater than 0 and summation I varies from 1 to r hi of theta equal to 1 for all t greater than 0. Here mu ij theta of t is the grade membership of theta ij in mu j. Let us consider x1 of t belongs to x1 minimum, x1 maximum, that is denoted by capital M1 and capital M2 and the following equation. So here x1 of t equal to h1 x1 of t M1 plus h2 x2 of t M2, h1 of t plus h2 x1 of t equal to 0, where h1 of x1 of t equal to M2 minus x1 of t divided by M2 minus M1. h2 of x1 of t equal to 1 minus h1 of x1 of t. Now, TS fuzzy system is denoted as follows. Here, A1 and A2, B1 and B2 are the system matrices. To investigate the stability analysis of our considered system, let us introduce integral type sliding mode control. It gives a well organized way to control problems. It has been extensively utilized to both complex and practical models because of the properties of sliding mode control. It possesses a depraved robustness in the opposition of mismatched disturbance during the reaching mode dynamics. In general, sliding mode control design has two essential processes. First, to construct a sliding mode manifold as a function of the system states so that the system limited to the sliding surface has attractive properties such as stability. Secondly, to construct an appropriate relay type controller to make the model state trajectories to the sliding switching manifold function and preserve it there for consequent time. Now, we propose a fuzzy sliding manifold as follows: S of t equal to integral 0 to t gx dx minus integral 0 to t gx summation I varies from 1 to r hi of theta of x summation j varies from 1 to r hi of theta s ai x of s plus bi kj x of s into ds, where the projection matrix is denoted by Gx and full rank matrix denoted by Nx. Also, the nominal part of fuzzy integral sliding mode control dynamics summation j varies from 1 to r hi of x of s and kj are design parameters to be obtained. The solution of x of t can be written as follows: x of t minus x of 0 integral 0 to t summation I varies from 1 to r hi of theta of s ai into x of s plus bi into u of s plus fm of x of s plus pwi w of s into ds. The following can be obtained by using the above equation 8 and 9. We get the equation number 10. By using sliding mode control theory, s dot of t equal to 0, then we get the following equivalent control, which is denoted by equation number 11. By substituting equivalent control in the system 7, we get the following fuzzy sliding mode dynamics, which is denoted by the equation number 12. Given free specified positive scalars mu and gamma and norm of hp of theta t less than pi p, here p belongs to R, the system 12 is called passive if there exists a matrix bi greater than 0 and I belongs to R and approximately dimensions matrices n and m such that we get the following inequalities 13 and 40. So the system coefficients and the parameters denoted by the following relations. Let us see the proof of the theorem. So based on the properties of the membership functions and for any matrix n and n transpose, the following equation is true. So it plays the vital role to investigate the stability analysis of our considered system. Here we choose time dependent fuzzy Lyapunov function v of t equal to summation I varies from 1 to r hi of theta of t x transpose of t p x of t. So let us take the derivative of the Lyapunov function. So we get the equation number 16. For any matrix, let us consider the following zero matrix. By using the zero matrix and the derivative of the Lyapunov function, we get the following: v dot of t minus I of t less than or equal to summation j varies from 1 to r hi of theta of t zeta transpose of t gamma ij zeta of t. Here psi of t denotes 2 omega transpose of t y of t plus gamma omega transpose of t omega transpose of t, and psi of t denotes x transpose of t x transpose of t omega transpose of t. By using the Kerr complement lemma, we get the following: v dot of t minus I of t less than or equal to 0, less than or equal to 0. So we derived the theoretical results. So we are going to verify by using the following simulation example whether our derived theoretical result is stable or not. For that, let us choose the following example. So here the system matrices are assumed by C1, C2, B omega 1, B omega 2 equal to D1 and D2 and Fm. By solving linear matrix inequalities, the above theorem, by using the above parameters, we get the following control gain matrices K1 and K2 is we have chosen here. The concerned sliding mode surface in equation number 8 obtained as follows. Here, the constant matrix Gx satisfies Gx and Bx as a non-singular matrix. It plays major role to get the control gain matrices. The system parameters we have taken from the existing literature. So J, R, rho, pi, Le, LQ, LD, RS, NP, M1, M2. Moreover, the fuzzy sliding mode controller, we get the following relation U of t, which is denoted by equation number 21. Here, we have chosen rho of t equal to delta plus 0.2 into x of t, gx, bx plus norm of gx, bwx plus norm of w of t. Here, the tuning parameters lambda equal to 0.4 we have taken. Moreover, the disturbance signals we assumed w of t equal to 0.9 divided by 1 plus t square. So, by using the above parameters, we get the following response of the states for TS fuzzy BMSG based wind turbine system. So, figure 2, we get control input of the signals. From the figure 3, we get response of the fuzzy integral sliding surface function S of t. Figure 4 indicates that response of the sliding surface manifold S1 of t with a different delta. Look here, when delta equal to 0.5, so we get this trajectory. So, when delta equal to 1, when delta equal to 1.15, when delta equal to 2.0, when delta equal to 2.5, we get different trajectory. When delta values reduces, so it is reaching to 0 quickly. So, this stability depends upon the stability which is included in the control signal. Similarly, we get response of the S1 of t with different deltas. It can be clarified that the it can be clarified that state response of the model shall start on the sliding surface manifold from the first time instant and can be driven onto a any neighborhood near to 0 in a finite time, which is shown as figure 3. Moreover, figure 4 to 5 describe the comparison of the sliding surface manifold with a different delta. From the figure 4 and 5, it can be observed that the getting response are quicker when enlarge the value of delta and k, but it is noted that this may not true for all time since delta only limits the upper bound of the getting instance and nonlinear BMSG based wind turbine system different way. So, in order to describe the dynamic response of the system, the obtained solutions are plotted in figure 1 to 5 under the specified initial conditions for the state WQ, IQ, ID for the fuzzy integral sliding surface S of t and control input U of t. It has been shown these figures 1 to 2 depicts the existence of the matched disturbance and the external disturbance. The state variable x of t with the fuzzy integral sliding mode control is asymptotically stable. From figure 1 shows that the state trajectories of the concerned nonlinear BMSG model. Figure 2 describes the response of the control input vectors. Furthermore, the nonlinear sliding dynamics 12 can be a passive and asymptotically stable under the constructed fuzzy integral sliding mode control law. So, it can be observed that the state response of the model shall start on the sliding surface manifold from first time. So, it can be observed that the delta depends on sliding surface function. So, now let us conclude about our presentation. Fuzzy integral sliding mode control for PMSG based wind turbine system has been investigated by using fuzzy Lipno approach, which includes the information of membership functions by using orthogonal complement and proportion theorems. The sliding manifold has been constructed. The sufficient conditions have been established for the concerned TS fuzzy sliding mode dynamics to ensure asymptotical stability. Furthermore, a fuzzy integral sliding mode control has been synthesized to maintain the system trajectories into pre-designed fuzzy sliding mode. Finally, the numerical example has been given the efficiency of the anticipated PMSG based wind turbine system. So based on the our theory and numerical example, so in future, so we can extend this work into by using nonlinear decoupling method and multi-instant homogeneous polynomial approach, so we can extend it. So now, so these references we have taken to give this presentation. So the first one is the document, and the second and the third is the books. We can get it if you need further clarification. So you can refer these links. Okay, thank you very much. Have a nice day.